Morning, everybody, or good morning, Sandhya and Travis.
Morning.
Good morning.
Kind of lonely here today.
Yeah, a little bit.
Okay, so do you have any 3-6 questions? I know that was loaded, kind of some long algebra again, but the main, yeah. Do you have any of the 3-6 problems you'd like to take a look at? Morning, Maria. I got that. It was quiet, but I heard a little tiny bit from you. So I had just asked Maria if there are any questions on 3.6.
Maybe question 39.
39? Okay.
Sure.
So let me take a look at that. So first of all, what you're looking at here is the problem is that beginning part, 1/2 times parentheses 1/2 times the natural log of x plus 1 over x minus 1 plus the arctangent of x. That's the problem. And quite a bit of algebra can be done before you take a derivative. So what's happening here in the beginning part is, as you know, when you so this 1/2 can be pulled outside. That, you know, this 1/2 right here can be pulled outside, making it 1/2 times 1/2, which is 1/4. Now, what they did in this next part is use the law of logarithms. When you take the log of a quotient, that's the log of the numerator minus the log of the denominator. And then, okay, so why this 1/2 is here is because they did the distributive property. You know, 1/2 times term 1 plus 1/2 times term 2. So anyway, that was the algebra done to get ready to do the derivative. Okay, now the derivative. So to take the derivative of the constant 1/4, you leave that there. What's the derivative of the natural log of x plus 1? As you know, it's 1 over the natural log of the thing you were, it's 1 over that thing you were taking the natural log of, minus the natural log of x minus 1, 1 over that. Okay, then it came time to do, now we got this 1/2, and the arctangent of x, which I didn't have you memorize, but the arctangent of x is u prime, which in this case, x, the derivative of x is 1. So 1/2 times 1, and then over 1 plus x squared. So this basically comes from the derivative of the arctangent. So then the rest of the problem is getting that together with a common denominator, and I don't know, that I can do that if you want, but
I guess that's fine. That was the only part that I did, was just, I think, the common denominator part that I screwed up somehow. But
you did?
Yeah, that was the only part of the problem, and I didn't have right here. At least
okay, then we better do it. All right.
Yeah.
So let's see if I can make some space here. Let me grab this part right here.
But for that, you would just need to multiply the top and the bottom by the opposite one.
We'll do it. I just gotta just give me a second to grab it. And we'll go off to the side here and do it. Okay. So bring that in. Yeah, so we were at this point. Okay. So we still got our 1/4 out in front. This next part, I'm going to spread it out. Well, all right. So basically, what's x plus 1 times x minus 1? That's x squared minus 1 squared. So I got to think about this. You want to get common denominator for all three. Yeah. So let's just let's see. What would be the best way to do this? X plus 1 times x minus 1 is x squared minus 1. Not quite what this is. So it looks like we need, well, it's a lot. It's going to take a long time. Maybe we should do this. This could take 20 minutes.
Yeah, we don't have to do it. That's fine.
So I think if you want, maybe we could do it privately, but that's really all that's left on this problem.
Yeah, that's fine.
Okay. Anyway, as you can see, they got the answer 1 minus x to the 4th. Yeah. So what they did is they said the common denominator, they multiplied top and bottom by x squared minus 1. Yeah. Anyway, it's a lot. That's how it comes out. Another one on 3/6. You know, what we have today is the beginning of lesson 3/7. It's good. This is a 2-day lesson coming up. I will just say this: if you look at here, here's my homework, at least the beginning of it. And when you look at it more closely, you realize a lot of these are what? I mean, there's a fair amount of algebra that takes place here, and so it's a little unfortunate because what I wanted to do, it's really what we did in lesson 3/6 is what we're gonna make use of today. And what we did in 3/6, do you remember, was called implicit differentiation, where we differentiated x, y. We did both of them, and we had to pay attention to what we were differentiating with respect to. So, okay. So the lesson is called related rates. Just to give you an idea what related rates are, it's pretty much word problem situations where you have two things that have their own rate, but they're related. For example, if you look at this, let's see, maybe I have to get the pictures out of here. Trying to remember. There we go. So you've got this, here we have a picture of a guy down, his little guy down here, and there's a lamppost here, and there's a shadow. And as he moves to the right, we're going to keep track of his distance, which you see right now, I think you can see is 17.6, and the shadow length, which is represented over here at the current time is 8.8. So when we put this in motion, you can see both rates are changing. And I'll just let that keep running. It goes back to the beginning again and starts over. Up in the graph in the top right, you can see each rate, and you can see how they're both related. Okay, and over here in the corner, it's all based on time. So what we're going to do is we're going to be differentiating with respect to time today. So we're going to be doing d dt. Otherwise, it's what we've learned before. So let's jump right into an example. Except I'm going to do my own version of it. So we've been told that y equals x squared plus 3. Okay. Now what we're going to do is differentiate this with respect to time. So notice there's no t in the equation. So that means both y and x are going to have to be, we're going to have to do the chain rule on that. And then we're also told that x is 1 and dy dt is 2. So when we get started, we just literally take the derivative of the whole equation with respect to time. Notice that dt on the bottom. Okay, so on the left, the derivative of y with respect to t. On the right, 2x, but because x is not t, I got to do the chain rule on that too, dx dt, and 3 goes away. Okay, well we can, so that's our derivative right there. That's our derivative. Now, go back up to the problem. It says find dy dt, which we've solved for, when x is 1 and dx dt is 2. So we just literally plug in a 1 for x and a 2 for dx dt, and we do the arithmetic. So what is dy dt when x is 1 and dx dt is 2? 4. So you're going to find, once you've set these problems up, they're not very, they're like, it's simple arithmetic really to get done. You just have to remember, how do you differentiate implicitly? And of course you have to know the equation. In this case, they handed it to us. They said y equals x squared plus 3. Okay, let me put that back. Let's take a look at example 2. Okay, so we have a sphere, and the rate of change of the sphere volume is what we're supposed to find if dr dt is 3 and the radius is 4. Sorry, that got covered up a little bit. If the radius is 4. So now they didn't give us the formula. You guys remember? What's the volume of a sphere? You remember the formula for that? Maybe not. It's volume equals 4/3 pi r cubed. Okay. And once again, we're differentiating with respect to time. So evidently what we have here is like a balloon being filled, and it must, I don't know, there must be air leaking out, or it's being filled, because you see up on top it says dr dt equals 3. That means for every second, the radius is increasing 3 inches, 3 centimeters. So this thing's in the process of being blown up. Okay. And they're telling you that the current radius is 4. Okay. So now it's time to do our implicit differentiation. We take this whole equation and we're going to differentiate with respect to time. So on the left, dv dt, the derivative of the volume with respect to time, equals, and here we can use the power rule, right? 4/3 pi r cubed, 3 comes down, 4/3 times 3 is 4. Pi is a constant. R, reduce the power by 1, but because r is not t, we have to do dr dt. Okay, so that's there's our derivative. That was simple. Now, plug in what you know. dr dt is 3, so we're going to plug in a 3 right there, and r is 4. So 4 squared is 16. 4 pi 16 times 3. And so at what rate is the volume of this sphere changing when the radius is 4 inches? Is 4 whatever, we don't know the actual amount. We don't know the label. It's 192 pi. So let me just pause. Any comments or questions? So really, this is not very difficult. It's just a matter of adjusting. This is the first time we've differentiated with respect to a third variable, time. And this often happens in physical problems. As time ticks on, what's the rate of change? And that's basically what we're finding out here. Okay, let me pull that back up again. Okay. So what I've done is I've developed this framework. I call it a framework. It's like a template for doing problems like this. Maybe a little bit corny, and if I was better at acronyms, I might have come up with a better technique here. So, because if you take the first, identify variables, I, relate the variables, R, chain rule, C, substitute and solve, S. Together, they form the word IRCs, which, like I said, I'm not very talented at coming up with that, but this will work for just about every problem. Okay, so I'll show you how that can be used. So let's take problem number 1. And I'm going to do this to the right here so that you can see it being done. Okay, so the problem up on the top right there, in exercises 1 to 4, assume that x and y are both differentiable functions of t. Find the required values of dy dt and dx dt. So in number 1a, we're trying to find dy dt, as you can see, when x is 4. So the first thing we got to do is identify our variables. Okay, this is kind of, that doesn't mean a whole lot here. Obviously, it's x and y. And the time, of course, is changing. Relate the variables. Well, they've already done it for us. That's this part. I'm going to rewrite it. The square root of x as x to the 1/2 power. Okay, so, and we don't, maybe I shouldn't have put t in there because in the variables. So I'm going to go back up there, erase that. Because time is kind of what, the independent variable, so we didn't really need that. So we've got two variables, we've got them related. There's another thing given up here on the top. We're told that what? X is 4. See, we're told that right there. And we're also told that dx dt is 3. So those are all gotten from the problem. All right. So I haven't done anything yet. All I've done is just kind of summarize what's been given. Now, take your equation, which we have right here, and differentiate with respect to t. So, on the left, so, I mean, we're doing this. We're doing the derivative with respect to time of x of y equals x to the 1/2 power. And what is it? Well, it's dy dt. And this is, of course, 1/2 x to the negative 1/2. But again, because we're doing it with respect to time, we have to use the chain rule on x too. All right. I know we could simplify this, but let's just leave. We don't have to worry about simplifying today because the last step is substitute. So let's put the given information in. dy dt is what we're supposed to find. We know what x is. X is 4. What's, yeah, I mean, this is 1 over what? The square root of 2? Oh, this is 1 over 2 times the square root of x, right? This thing right up here. Maybe I should have rewritten it. But anyway, what is the square root of, now when x is 4, the square root of x is 2, and you get 1/4, right? 1 over 2 times 2, 4. And then dx dt was given to us, 3. And now we got this really tough arithmetic job. I'm joking. So what is dy dt when dx dt is 3 and x is 4? 3/4. So this little template can help us, can help set us up. Otherwise, you look at the problem and you're like, wow, where do I begin? What do I do first? This little template I have found in the last last 6 years I've been using it. Seems to really help with students quite a bit. Okay. Anybody have a question? We're gonna just keep doing examples, and we will spend another day on this tomorrow. All right, let's take example number 5. So I should go to the book, and we'll pull this out. We'll do it ourselves. So let's go to the template. Okay, so here we go. We got a blank template here. Now look at in your book at number 5, please. Okay. And I got to look at my book. Okay, number 5. So this time we're told we have, let me grab this. Sorry, it's going to take a few extra moments here. We're going to grab this problem. Okay, now we'll come back. We'll pull that in. And we'll have the problem handy. Okay, so identify the variables. Well, you can see we have x and y again. All right. We're also told that dx dt is 2. And we're also told in part A that x is -1. We're going to just do one part at a time here. Okay. And relate the variables is already done. That they gave us this equation. So that's already done. So it's time now. What's the difference? So now what we need to do is take the whole thing, the derivative with respect to time. So that's our job. Okay, let's do it. On the left, we have dy dt. Yes, Sandhya, I did hit record, thankfully. Okay. So it's all going to be recorded for us. So dy dt, and then this is what, 4x? But because x is not t, I got to do dx dt. And the derivative of 1 is nothing. Solve for dy dt, because that's what they asked us to find. And we already have it. Here's our derivative. Now, substitute and solve. So what do we know? We know that x is -1, so dy dt equals 4 times 1, and dx dt is 2. And what is the rate of change of y with respect to time when x is -1 and dx dt is 2? 8. That's part A. So how do you find B? Well, okay, B, we just have to take our, this is really the key part of our answer, that derivative. And now, instead of substituting in a -1 for x, now you're going to plug in x equals 0. The dy dx, the dx dt stays the same. So for part B here, let's do that over here to the right. Dy dt equals 4. And this time x is 0. And dx dt is still 2. Of course, the answer now is 0. So part B, the answer is 0. And then you could do the same thing, the same type of thing for part C. All right. Questions? Yeah, this is being recorded. Let me get rid of those on the bottom. All right. Let's do another one. Coming back up. Yeah, let's take a look at number 6. Only again, I want to do it with you. So, number 6. So, go down here. Sorry, I know this looks a little disorganized. So we're going to take our template, and now we want to do number 6. So from our book, number 6. So there's number 6. Okay, at least the problem from the book. So now, okay. And by the way, the general directions for number 6, let's just look at the book. It says, find dy dt for the given values of x. So find dy dt. That's the ultimate goal. Okay, now back. So you can see that we can say dx dt is 6, given right there. And for part A, x is -2. We'll do part A. And the relation of the variables is already done. Y equals 1 over 1 plus x squared. Okay, so it's time to do the chain rule. We got to differentiate this with respect to t. So dy, let me redo that. There we go. So the derivative with respect to time of that whole equation, y equals 1 over 1 plus x squared. Okay, this one's a little bit more challenging. So when you take that derivative on the left, you get dy dt. So what do we have to do on the right now? We got to do a quotient rule, right? So denominator times derivative of numerator minus numerator times derivative of denominator. And remember, we're doing this with respect to time, so even x, we have to do the chain rule on. And then that's all over denominator squared. Okay, of course, this part times 0 here, that's gone. Okay, so basically we've got our derivative. And let's just rewrite it a little bit. dy dt, and on the top there, that whole thing is being subtracted. So -1 times -2x is 2x dx dt over 1 plus x squared squared. Now substitute and solve. So we know what dx dt is.
Is it -2x on the top?
It's you see right here, it's -1 times -2x. Because you're subtracting that whole thing. When you're subtracting a -2x, you're actually adding a 2x.
But I thought it was -1 times 2x. That'd be -2x on the top.
Isn't it? Oh, it's times
It should
2x.
be.
You're right. I thought it was times a -2x. You are correct. Thank you.
Yeah.
Okay, so now plug in. We know what x is. It's a -2. We know what dx dt is. It's 6. So what do we get? -2 times x is -2 is 4 times dx dt all over 1 plus x squared. 1 plus 2 squared is 4, and 4 squared, I mean, yeah, 1 plus 4 is 5, and 5 squared is 25. So 24/25 is the solution for part A. So really, it's kind of cool because when you get all done with your derivative, all you have to do is substitute what's been given, and you can find what you've been asked to. So for part B, same thing, only this time x is 0. You can go through and calculate that out. All right, questions? Let's go to the next one. Next one I wanted to look at was number 12. Ah, yes. Okay, so now we got more of a challenge, and I'm gonna I'll show you the problem I've got right here. So here's number 12. Area. The area included the included angle of two sides of a constant equal length s of an isosceles triangle is theta. So I made a drawing here. So it's an equilateral, it's an isosceles triangle, so two sides are the length s, and the angle included between them is theta. That's what the problem's telling you. Okay. It says A, show that the area of the triangle is given by A equals 1/2 s squared sine theta. Okay, so that's part A. So what I did is I sketched in a height, because I'm assuming at the moment, what do we know? The area of a triangle is 1/2 BH. Okay, so I sketched in, as you can see, a height to one of the sides, all right, which is perpendicular. And using our 1/2 BH formula, okay, can we use a little trig here? If you take h over s, okay, I got to think about this. Hang on a minute. What did I do there? H, the sine of theta in that little right triangle is the opposite over the hypotenuse. So in this triangle, the side opposite theta is h, and the hypotenuse is s. So do you see that? Sine theta equals h over s. Solve it for h. So if I multiply both sides by s, I now have another name for h. S times the sine of theta. So now I could go back to my BH over 2, and using my new h, I get this formula. Area equals 1/2 S. Okay. Why did I do that? Because the base is half of S. That's why, that's where I'm running out of colors here. Let me plug in something different like green. So do you see that that came from hang on. Got to make sure I use the right thing here. 1/2. So here's the substitution for H. Okay. Oh yeah. So 1/2 base times height, and the base is S. So I just substituted S for B right here. Okay. And then if you just put it together, S times S is S squared, you can see we did it. We showed that the area of the triangle is 1/2 S squared times the sine of theta. So we haven't done no calculus here at all in part A. All right. Part B. Here's where the calculus comes in. If you look up on the top, the angle theta is increasing at a rate of 1/2 radian per minute. That's interpreted right here. Maybe I should use, so in that green color I just circled, do you see that? It's saying, hey, this angle is increasing, so d theta dt, over time, it's increasing at a rate of 1/2 radian per minute. The current angle, it says, find the rates of change of the area when theta equals pi over 6. And then secondly, part B, do it, or part 2, when theta is, so let's just do one at a time. So theta is pi over 6. And what you're supposed to find is, what's the rate of change of the area? D capital A dt is question mark. Okay, so now we've got our variables defined. Right? I mean, the problem tells us d theta dt is 1/2 radian per minute. The angle we are currently at, that we're supposed to investigate, is pi over 6. And you're supposed to find the rate at which the area is changing, the a dt. Okay. Now, let me move this thing up. Well, we start with our formula from part A, which was A equals 1/2 S squared times the sine of theta. So there's our formula, right? I got to change colors. Let me use red. So here's our formula right here. Okay. Now, we're going to differentiate with respect to time. So on the left side, d a dt. Okay. Hang on, I'm just trying to see what I did here. 1/2 S squared times the, well, we know that the derivative of the sine is the cosine. Trying to see what happened on the left with S squared. Hang on a minute.
Shouldn't this been a product rule?
Hang on. Yeah, that makes sense. Oh, because, so S is a constant. Okay, I got it now. I mean, in a this triangle is not changing shape, not changing size. So S in this problem is a constant. So that's why, because this is just a big old, like a number here, it's the constant gets left alone. Yes, somebody trying to speak up?
No, I was saying, yeah, okay, that makes sense.
Okay. So because that's a constant, I didn't do anything. And the derivative of the sine of theta is the cosine of theta. But I still have to do the chain rule on theta because that's not t. So dt. Now here's where I do the substitution. Remember, up above we were told, so s 1/2 s squared, that's another way of writing it, s squared over 2. What's the cosine of pi over 6? Pi over 6 is 30 degrees. The cosine of 30 degrees is square root of 3 over 2. And then d theta dt, this part, that's the 1/2 from right up here. And then it's just a matter of bringing them together. And we can, that's as good as we can do because we don't actually know the number that S is. So let's go through that again. We were supposed to use the equation from part A, which they asked us to prove, and we did. That's this A squared, I'm sorry, A equals 1/2 S squared, 1/2 S squared times the sine of theta. Okay. On the left, dA dt. On the right, constant, 1/2 S squared. Derivative of sine theta is cosine theta. Chain rule, d theta dt. Then it's just a matter of substituting in theta is pi over 6. So the cosine of pi over 6 is square root of 3 over 2. And theta, d theta dt is 1/2. And then just multiplying it out. Okay, so that's part A. Well, part B, the second part of part B was to do it with a different angle. Sorry. And then we would do it all over with pi over 3. Pi over 3 is what? A 60-degree angle, and then that, yeah, I didn't do that. All right. So as you can see, that one was more complex. Does anybody have, do you want to go over any part of that? Okay. Let's see if we can do one more here. Let's take number 13. Okay, and for this one, I'm going to make we'll go to our framework. What was that, number 13? Yeah. Okay, number 13. And I'm going to pull that problem in from our book. Okay, so here's our problem. Make it a little bit bigger. Okay, the volume, the radius r of a sphere is increasing at a rate of 3 inches per minute. Can you interpret that right away? So that means dr dt equals 3. Find the rates of change when r equals 9. That's given. And then we'll do, 36 you can do. Okay. Now, notice they didn't tell you anything else. So guess what you're going to have to do? You got to come up with a formula for the volume of a sphere? Well, we've already used it today. It's V equals 4/3 pi r cubed. So they're assuming, you know, a little bit from the past. Okay, so guess what? We need to differentiate this with respect to time. So derivative with respect to time of 4/3 pi r cubed. Oh wait, I should really, I forgot the v. So let me try that again. Okay, so this would be v equals 4/3 pi r cubed. Okay, so on the left we have dv dt. On the right, power rule, 3 times 4/3, the 3's cancel and you get 4 pi r squared. Our variable that we have to differentiate with respect to time, the r dt. Okay, just erase my stray mark here. All right, so are we ready? We can, we've got dv dt solved for. That's what we're supposed to, you know, I should have put that up on top here. The one other thing I would list up here is that that's what we're trying to find, dv dt. And we've got it already solved for down here. So all we need to do is substitute dv dt 4 times pi. And r is 9, right? So r squared is 81. R is given right here as 9. So r squared is 81. And the r dt is 3. So then we got to just do some multiplication there, and we get our answer. So what is that? 81 times 12. So 972 pi would be our dv dt. Okay, so as you can see, this framework should really help you with problems. Kind of get all your variable stuff on the top. Then the really important step is you need an equation. And either they will give you one or you will have to come up with it. Like in this case, we had to know what the volume of a sphere was. I mean, they're real basic ones. Yeah. They're ones you probably have had since geometry class or before. Okay? So once you've got that equation, well, then the next step is differentiate with respect to time using implicit differentiation. Follow your rules, and when you get down to the bottom, solve for whatever, in this case, dv dt. We didn't have to do anything special for that. And then substitute in what they gave you. Result. So, okay, so at least we have an introduction to this, and I'd like you to study it a bit, maybe start doing the problems. I'm going to show you what the assignment is eventually going to be. It's right, you know, it's the 3-7 here. 1, 12, you know, 2, 3. About 12 problems to do. But we need at least another day on this, and that's what I'll be doing tomorrow in class. Go ahead.
No, I was just saying that sounds good.
Okay. Anybody have a comment, question? Well, thank you. And nice having you three here. I wish we had more of the class here, but
yeah.
I'll see you tomorrow.
All right. See you tomorrow. Have a good rest of your day.
Thank you. You also.
Thank you.